So Rosemont Mine is obviously a controversial subject regionally and in the watershed in particular. But I'm really going to focus on one particular aspect of the mine and its potential environmental impacts if it were to be approved and operate. And that relates to its hydrologic impacts, particularly on the groundwater system of the Cienega Creek watershed. So this is just an outline of the talk. I'm going to talk about water budgets and then the hydrologic setting, the potential impacts of the mine's operation, and then talk particularly about the models that were built by 3 different consultancies, one for the county, 2 for the mining company, the choices they made, and then looking at those results and sort of understanding what that means for how, if the mine were to be approved, what the long-term groundwater impacts would be. And so, right, the first basic concept is really just a basic water budget, right? Any watershed has a water budget of how much rain comes in, and then where does that rain go? Where does that precipitation go? Does it go back to the sky as evapotranspiration? Does it leave as discharge? Does it provide groundwater that discharges or provides support for other aquifers? And then also the groundwater that might come into the watershed from outside the boundary, this groundwater in. But in particular, when we talk about groundwater systems, we have something called the concept of capture hydrology. And this is sort of at the core base of the long-term hydrologic impacts of the mine. Right, pre-development, before we started groundwater pumping, before a mine was constructed, you know, in Arizona, we oftentimes consider this pre-development status 1945 or before, because before 1945, significant groundwater extraction was relatively limited in the state of Arizona. But pre-development, recharge and discharge in any given groundwater basin are likely to be relatively balanced. Maybe not perfectly on a year-to-year basis, but on a long-term basis, how much water is discharging out of a basin, out of an aquifer, has to equal what's coming in. And then within this concept, right, we have, well, where was that recharge coming from, right? We have in basin and range aquifer systems, like what we see in Tucson and kind of like what we see in Cienega Creek, but Cienega Creek is definitely more complicated than that. We have sort of processes occurring in the mountains, mountain front or mountain system recharge, but then we also have stream water losses from streams, losing streams that are recharging aquifers. We can also, the discharges then include evapotranspiration from riparian areas, stream flow, and then underflow, right? Groundwater flow that's leaving the basin in through the subsurface, okay? But in the pre-development concept again, right, this recharge, the losing streams, the underflow, the mountain front recharge have to equal the gaining streams, the underflow out, the gaining stream discharge, the underflow out, and the evapotranspiration. Okay, but now you've developed a watershed. Okay, you've started to pump, or in the case of the Rosemont mine, what you're doing is you are extracting water from the subsurface through the remaining pit. During operations, they'll be pumping, but one of the keys with the Rosemont mine is the pit will continue to exist forever, and that pit will represent a hydrologic sink in the watershed. That the evapotranspiration from that pit has to come from somewhere, and so it, in many ways, simulates a well, pumping water. But right, if you increase discharge from the aquifer by pumping, this Q term here, okay, there are really only 2 choices. You can either increase recharge into the aquifer or you can decrease discharge. That's essentially it. There may also be and would also be changes in storage, but on a long-term basis, in any basin that has surface water expression of groundwater discharge, that pumping is going to have to either be represented by an increase in recharge, typically by, say, gaining streams into losing streams, or by a decrease in discharge. And the decrease in discharge is more of what people think of, whether it's pumping near the San Pedro, the drying out of the Santa Cruz River in Tucson, right? That decrease in discharge is represented by that loss of surface waters. Okay, and it's, capture really ultimately isn't a fancy concept, right? That if you had if you have a water budget for the watershed, you have recharge plus the change in recharge minus discharge minus the change in discharge minus the pumping is equal to the change in storage over time, okay? But if you remember that recharge equals discharge, then you can see that the change in recharge and the change in discharge have to equal the pumping plus some storage term, okay? But this term, change in recharge and discharge, is called capture. And ultimately, the people who are constructing groundwater models in the Cienega Creek Basin are focused on, part of the focus of those models is what is that capture, and also critically, where is it having an impact in the system? Okay, and that impact, that capture of water can come in two ways. One, a well can pull water out of a losing stream, okay? Or more typically, a well is intercepting water that was recharged elsewhere before it arrives at a gaining stream, okay? And that loss of recharge out through the pump, so to speak, or in this watershed's case, a mine, will reduce the level of water in the water table. And in our case, oftentimes the first indicator is that you're losing trees because the groundwater table is dropping. Okay. So ultimately though, right, you have a pump, it creates a cone of depression, a pit in the groundwater. One advantage of the Rosemont mine, you know, in terms of thinking about it, simulating it, the pit is easy to visualize because there will literally be an earthen pit from the construction of the mine. But once those cones of depression exist, you can see, right, you can either, you started at this dotted line, the original recharge or discharge, and you're going to these larger blue arrows. So you can either increase recharge or decrease discharge or some combination of the two. In the case of the Cienega Creek Basin, the main result is essentially a decrease in discharge of the groundwater system into surface water systems. Okay, so on to sort of the main piece of the story here, the mine itself, right? So this is a map from the Arizona Daily Star, sort of describing the location of the proposed mine, right? So Tucson's up here at the upper off the screen, right? Cienega Creek, and then Davidson Canyon. Importantly, the mine is going to be in the drainage of Davidson Canyon, particularly the Barrel Canyon drainage of the Davidson Canyon drainage. And the mine itself is this red circle here, and then the tailings are these surrounding areas. So, right, the mine has an impact on its own footprint, but then all the rock that's excavated has to go somewhere and is represented as a waste pit outside of the mine. You can see it's relatively close to Highway 83. And one of the perspectives to have is that if you go to a couple of the turnouts on Highway 83 down to Sonoita, you can sort of look back to the ridge of the Santa Ritas that stretches north, and you see this sort of image. And actually, some of the discoloration you can see in these hills is indicative of the underlying mineral content of the rock that ultimately is the rationale behind the mine. But you know, that landscape post-mine would look something like this, with a large pit near the ridge top and then large systems of tailings on the eastern side of the pit, right? Mining is the #1 source of waste in the United States, and it's literally waste rock. They extract the rock, they process it in a number of ways to extract metal, and then the waste rock has to go somewhere. Now, the position of this watershed and the mine, right? The mine is right here on the ridge. This white line that you see on this image from a map made by Meadmeyer at Pima Association of Governments is the boundary of the active management area. So the mine and most of the Cienega Creek watershed are outside of the Tucson active management area that regulates groundwater pumping, that says within the AMA, pumping has to equal recharge, at least on a long-term basis for the watershed, okay? This map also sort of notes with these purple, the wildlife corridors, and that's obviously, right, another impact of the mine is this significant sort of land cover impact, land use impact on a major ridge that is a wildlife corridor. Now, I'm not talking about today, I'm focused on these hydrologic impacts, but you can see the mine is on this ridge, and then again, the creek, Davidson Canyon here, and then farther away, Cienega Creek, both could potentially be impacted. The hydrologic question the groundwater modelers were trying to answer was when and where might that happen, and to what degree. Okay, so again, a variety of different groups, really three. Tom Myers worked for the county, built a groundwater model, and then Tetra Tech and Montgomery & Associates. Tetra Tech, a major national consulting firm. Montgomery & Associates, a fairly large firm now, but sort of born here in Tucson, and has their main offices here in Tucson, right? But they build groundwater models, and this red boundary here represents some of the modeling domains that they utilized to look at what the impact of a pit and the mine's operation would be. Okay, now the setting here is that this mine is also close to the Las Cienegas National Conservation Area, which has a number of recreational activities, but also has a almost fully intact ecological system aquatically, which is all but non-existent elsewhere in southern Arizona. There's both native fish that are threatened or endangered, as well as amphibians in the watershed. And there's been a lot of effort to preserve the riparian corridors, the cottonwood gallery forests, which again are a relatively threatened ecosystem in the state of Arizona. It's estimated that upwards of 90% of the cottonwood willow riparian area that existed at statehood is no longer present in the state of Arizona. Okay, and there's this little guy, the Chiricahua leopard frog, that our own organization, the Cienega Watershed Partnership, has worked with a variety of organizations, including the BLM and then a number of scientists, to restore. And just to give you an idea of that restoration effort, right? When those restoration efforts started, there were some small populations of those frogs shown in circles within the watershed. But over time, through efforts to eradicate bullfrogs, improve habitat conditions in cow tanks, among other things, right? The frogs are significantly more extensive and much larger domain, much larger distinct populations of frogs. And obviously, frogs depend on perennial water. And if any activities in the watershed affect the existence and amount of perennial water, particularly from groundwater springs, which have been shown to be key for helping the frogs overwinter and protect against the chytrid fungus that's been killing them, indicative of sort of the effort in this area to maintain and improve the intact ecological integrity of the watershed. Okay, but ultimately, one of the questions about the mine is long-term, what effect will it have on perennial intermittent streams like Cienega Creek and Davidson Canyon? Okay, and one of the pre-existing concerns is that the stream has been drying out. So this is, again, a figure from the Arizona Daily Star, but based on data from the Las Cienegas National Conservation Area, right? This is showing the total length of the stream that is wet. Okay, the simplest biological observation to make is a wet stream can support species that a dry stream cannot. So the less wet stream length we have, the worse things are. And you can sort of see here, the lower creek has had a decline. The lower creek is the county preserve near Interstate 10, the Gabe Zimmerman trailhead region of the creek. Has the wetted stream length has declined over time. There's been some mild declines in the upper Cienega within the watershed. And then on a longer term basis within the Pima County Preserve, you can look back here to the 1980s and 90s for when we had a relatively wet climate in the 80s and early 90s. And you can see the flow length was relatively long. Through the preserve, there was 7 to almost 10 miles of wetted stream length. In more recent years, there's only been 1 to 2 miles of wetted stream length within the county preserve. So the system has been drying out, probably from a combination of this climate shift that we've been in a drought now essentially for more than 20 years, been experiencing this last year, a more severe stretch of that drought, but also probably due to existing pumping within the watershed. It's harder to document that, in part because of absence of data, but it's a difficult question to answer exactly why. Now, ultimately, the concern about the mine comes in and its hydrologic impacts come in two forms. One is the initial pumping. So this is inflow to the pit from storage or from discharge to the pit as modeled by, I believe this is the Tetra Tech model. And you can see, right, initially when the mine starts operating, there's a significant flux of water coming out of storage and discharge, draining into the pit. That's from the initial pumping operations, okay? And then longer term, the amount from storage declines, the amount from discharge to drain declines less. But this flux of water that has to go into the pit, that water has to come from somewhere. Now, some of it comes from storage, but long term, it has to come from ultimately declining water tables, the loss of storage, but then also declines in discharge of water to the surface. Okay. And, you know, the total flow to the pit is going to increase over time as the pit gets constructed. Okay. So we then get to what these reports say about the groundwater pumping in the basin. And this is from the Tetra Tech report. So right, the mine operates for 20, 25 years is the projection. And then following the end of dewatering, the pit's going to fill up with water. Okay, and that's important because as the pit refills with water, evaporation from that pit lake surface represents a continuous hydraulic sink. And it essentially, in all the models, the pit is a hydraulic sink, well, forever, until the pit fills in geologically, which is going to be thousands and thousands of years. And thus a capture zone, right? This pit is going to be capturing groundwater from the area around it. Okay. And then, so in the Tetra Tech model, they say predicted impacts to base flows in Davidson Canyon, Cienega Creek during operations were negligible and indiscernible compared to the accuracy of the model. But long-term, they do predict a decrease in base flow to Cienega Creek and to Davidson Canyon. Tetra Tech notes no losses were predicted in the reach identified as the outstanding Arizona water. Now, this is important. In the Clean Water Act, every state is allowed to identify what are called outstanding waters. Arizona has identified Cienega Creek and a portion of Davidson Canyon as an outstanding water. With the Clean Water Act protection, that therefore means that there can be essentially no adverse impacts on the water quality of that creek, sort of period. Okay, so that Tetra Tech model, again, here you're looking at the full domain, and it crosses the ridge into the Tucson Basin, which is going to be an important element. The Tom Myers model at the county ended at the ridge line, and that has an effect on how the model, the effects of the pit lake propagate through the basin. Okay, they also had to model all the evapotranspiration along the creeks and potentially to look at differences in that evapotranspiration. Okay, so right, there's a lot of detail that goes into these groundwater models, and I'm not going to get into that here, but there's a lot of different small decisions they have to make about where recharge occurs, how much it is, where discharge is occurring, what riparian ET is, what stream flow is, how much is coming out of the groundwater, etc. So it's not, you know, I can't do justice to all the work that these folks had to do to build these models, because it was significant, and a lot of the uncertainties that they have to sort of accept in doing so. Okay, so what do they show? So this is sort of the simulated drain flux that Tetra Tech found into the pit. And right, when dewatering starts, there's initially this very quick discharge of water for the dewatering, right? They have to remove the water to be able to dig the pit. And then subsequently, as they sort of mine new zones, they get to deeper depths, they widen the pit out, there's these other spikes. But roughly speaking, at the end of mining, it's about a 400 gallon per minute drain from the aquifer into the pit. Now, for reference, right, the limit on an exempt well, so a small residential well outside of AMAs in Arizona, is 35 gallons per minute. So this is a factor of 10 bigger than that, and in fact, maybe a factor of 1,000 bigger than a residence's typical annual pumping. Okay. So what do they find long-term in terms of these water balances? And these water balances ultimately are the key, right? So this sort of brown line at the top ultimately is the lake stage, right? And so the lake, at the end of mining operations, right, the lake starts at the pit's bottom elevation, which is about 3,000 feet above sea level. And the pit slowly fills with water, okay, until it's about an elevation about 4,300 feet above sea level. So the pit lake itself is forecast here to be 1,300 feet deep, okay. They then sort of simulate the groundwater inflow. And then importantly, right, the pit is open to the sky. So direct rainfall and snowfall onto the lake represents a significant amount of water, as does runoff that occurs within the pit down into the bottom of the pit, okay? So, you know, these three combined are sort of telling you that the ultimate flux, you know, of water sort of coming out of the, you know, evaporation has to balance it. So the evaporation is about 550 gallons per minute. These three lines, the pit wall runoff, the direct rainfall, and the groundwater inflow have to sum up to that evaporation, okay, to reach steady state. But you can see the time scale here, 1,000 years. So some of the impacts, right, the groundwater inflows are right away, but for the system to get all the way out to steady state, it takes a very long time. And that's true of groundwater systems. While capture is sort of an ironclad law, it takes a long time for groundwater systems to reach new steady states. They respond slowly. So just because you don't see impact in 5 years doesn't mean you won't see an impact. Okay. So this then is the model they have at the end of that 1,000 years of how much drawdown there will be in the aquifer. Okay. And it's one of the better ways we'll ultimately be able to compare these three models. And what you see, and I'll sort of preface the comparison to the others, what you see with the Tetra Tech model is, right, you have very significant drawdown near the pit. Makes sense. That's where the water is flowing to. Water has to flow downhill into the pit. But you then see this line of 10 feet of drawdown, really 5 to 10 miles away from the pit, and then of 5 feet of drawdown even further away. And notably, right, 1 foot of drawdown coming out all the way and intersecting Gardner Canyon, Empire Gulch. And in fact, with the Tetra Tech model, their surface water impacts are projected to most significantly impact Empire Gulch. So while in the Tetra Tech model, Cienega Creek itself is relatively modestly impacted, but impacted mostly through the upper basin, Davidson Canyon and that outstanding water reach that is close to Cienega Creek isn't impacted, okay? And the reason for that is that the model, in constructing their groundwater model, Tetra Tech identified a volcanic dike that occurs here, this pink line that's sort of halfway up the diagram. And they essentially, right, that dike, the cross-cutting nature, width, and length of this dike, however, suggests that it restricts groundwater flow, okay? So they essentially put an impermeable barrier in their model to limits how far down Davidson Canyon groundwater impacts occur, okay? And that really ultimately is a significant difference between the Tetra Tech model and the Montgomery model. Okay, so 1,000 years later, there are some impacts. You know, one of the keys that the Montgomery and Associates model folks point out is, right, more distant from the proposed pit, the extent of the groundwater drawdown is less reliable. Essentially, we don't really know the properties of this aquifer, right? It's a hard rock aquifer. There aren't a lot of groundwater wells. There isn't a lot of geologic knowledge about the nature of this aquifer. And so there's a lot of uncertainty about how quickly and how extensive the groundwater impacts would be, you know, beyond the pit. Okay, so now we'll move to the Montgomery model, which in many ways is similar to the Tetra Tech model, same sort of model domain, you know, higher recharge amounts than the Tetra Tech model, and, you know, ultimately getting to a slightly different result, okay? So they go through some of the same process of building in the stream, building in the recharge zones, making their estimates, understanding the nature of the aquifer as best they can, and ultimately produce a similar diagram, right? Slightly lower lake stage than the Tetra Tech model, you know, slightly lower groundwater inflows, you know, but again, precipitation, runoff, and groundwater inflow summing up to this evaporation when they get out to steady state at 1,000 years, okay? This is just an example of sort of the complexity of these models. This is a grid that's defining sort of the individual cells of the basin, if you will, that the model represents. Okay. And they also provide a really high resolution impression of what that drawdown near the pit is going to look like, right? There's going to be this tremendous groundwater sink at the pit. But another thing they provide is what the groundwater drawdown looks like 22 years after the mine is constructed, and then you'll see next sort of the 1,000-year simulation as well. It's actually a 200-year simulation. But again, here's the pit, and the drawdown is mostly associated right around the pit. Tremendous drawdown right at the pit, right 100 feet lower in groundwater table. But you can see already after the end of the mine operation, sort of the capture zone, the drawdown, moving down Davidson Canyon. Okay. And in fact, their model at 150 years shows that drawdown lobe moving more strikingly down Davidson Canyon. Okay. And so their model does in fact show impacts on Davidson Canyon to springs, not necessarily all the way down because they didn't simulate out as far, at least in this image. But, there's a shift, right? Both models essentially show an impact, a growing capture zone, a decrease in discharge of water to the surface from that capture zone because of that capture. But they differ in how long it takes. And critically, they differ in where. The Tetra Tech model argues it's going to be more up basin, Empire Gulch, near the Empire Ranch structures and upper Cienega Creek. The Montgomery model argues the lower part of the basin is going to get more significantly impacted. Okay, and then here you see out at 1,000 years, again, moving even further down Davidson Canyon with that drawdown. Okay, but you see not as much movement into the upper basin. Okay, so one of the things that spurred on Montgomery to model out to 1,000 years and the Tetra Tech model was Tom Myers, who worked with the county. So at the end of mining, groundwater levels at the pit will have reached their lowest level, but the drawdown is going to keep expanding. And one of the, Myers essentially assumes much greater ET than the other models. And then, but he argues, right, if you backfilled the pit, right, you'd create a flow-through pit and you'd cut off that evaporation discharge and thus eliminate those capture effects on a long-term basis. There would be a transient effect. The pit would expand and impact more and more of the basin over time, but filling the pit back in would eliminate this permanent hydrologic sink. It might cause other issues, but it would eliminate the sink. And so, right, Myers does a lot of the same things. There's an open pit, there's the tailing system, there's the runoff, there's the ET discharge areas of the basin. He has to represent that in a model. But then ultimately, he also he limits his forecast of how much drawdown there will be essentially through humility. It's like we don't really know where the drawdown is in some of these areas. So he focuses on Davidson Canyon and near the creek. And you can see he has drawdowns, 7,500 years. Basically, he models the system out to steady state. Drawdowns of a foot down into Davidson Canyon, a foot of drawdown close to Cienega Creek. And the difference between these blue and the red are if you backfill the pit or not, right? So the blue, you can see if you backfill the pit, the drawdown region dramatically shrinks. There's still a drawdown. You still had to dewater the pit, but by removing that long-term evaporation loss, you shrink that overall area that the pit will ultimately have an impact on. Okay, so just to sort of refresh your memory then, right? So that was Myers sort of doing that pit, no pit comparison and showing impacts on both upper Cienega Creek and lower. Montgomery really shows impacts on Davidson Canyon, and then Tetra Tech shifts, those impacts from Davidson Canyon into the upper basin because of the dike, which is hypothesized, and it's a reasonable hypothesis that impedes flow groundwater flow along Davidson Canyon and really prevents as much significant groundwater withdrawal impacts on the lower creek. Okay. So ultimately here, in part, I think there's a couple things I want you to take away from this, right? One is the iron law of capture. If you increase groundwater extraction, you will have an effect on surface water systems. You will have an effect on recharge and riparian systems. There is a matter of time and location, as these models show. But also, in comparing these models, right, each of these hydrologists has to have made different assumptions, right, about domain. Myers terminated his domain at the basin surface boundary. Montgomery & Associates and Tetra Tech did not. They extended to the Tucson Basin, and that allows both recharge to leak out, but also, withdrawals into the pit to come from more places. There's significant differences in the recharge estimates among the models. Myers had it about 7,000, and Montgomery & Associates around 10,000. Tetra Tech significantly lower. And then in riparian ET, Myers had lower riparian ET compared to Montgomery & Associates and Tetra Tech. And then, the pit lake is the key source of continuing capture. Myers says 670 acre feet per year, Tetra Tech 650. Montgomery & Associates had it at even lower, at a lower level. And then this rock dike that was inserted by Tetra Tech into the models was not included in the M&A and Myers models. And that dike presents an unknown degree. It might restrict flow. It may or may not. Tetra Tech hypothesizes that it does. And like I said, that's a reasonable assumption. But I think what's valuable to look at is how that shifts the model, okay? How that shifts the model's impacts. Instead of going downstream into Davidson Canyon, that dike instead has impacts in the upper basin to a more significant degree than the other models. Okay. And with that, I'll finish, and I'm happy to answer any questions. I see that Geeta has already queried me in the chat. I'm not sure of the plans. Geeta's question is essentially, what's the plan for the water pumped out during the digging of the pit? I'm not sure what the plans are. I imagine they will be used in mine operations because they're having to, one of the environmental compromises the mining company has made is that they're going to put wells near Green Valley and pump that water up to the pit for sort of the large scale mineral extraction, copper and metal extraction processes that they need to operate, and dust abatement and all those sorts of things. So I imagine they'll just use the water they need to extract for dewatering for the mine operations. Because I think discharging into existing channels would have, other unintended consequences, would be my suspicion. I haven't looked carefully at that aspect of the EISs because, as many of you are probably familiar, the impact statements for the mine are, tens of thousands of pages ultimately. So, are there other questions? So everything was perfectly clear to everybody. I asked this in my students in Zoom meetings, and
just takes everybody a little while to get their heads around what their questions actually are.
Same with my students. So, right, like I said, I think one of the things you want to take away, each of these modelers groups has had to make different decisions, but ultimately, right, the ultimate impact of the mine hydrologically on the long-term basis is going to be this groundwater alteration. This pit will be a hydrologic sink and will drain water into it, like I said, essentially forever. And that will eventually roll out through the basin. There are disagreements among the models of where, how long that might take. And then there are also people who say, well, what does it mean for something to have an impact 7,000 years from now? Which are fair, but I think it's good to know what the long-term impacts of a mine like this would be, because if a mine like this operates, the impact will be a forever impact. You can't really undo. Myers shows that if you refill the pit, you can at least decrease pit. So Richard Carl said, asks what processing on site, right? My understanding of the mine operation is that they're gonna extract the rock and then leach it and then leach it for metals, and then provide a concentrate that they're going to ship out to be smelted. The last I heard, that smelting was going to occur overseas, which I don't understand, but that's what has been planned. So yeah. Yeah, so Larry asked sort of how does the EIS reconcile the differences between the models? So, the statement has been made, in sort of the ultimate, sort of actions and permitting actions from the federal agencies that, these impacts the impacts that are forecast are either sort of outside their jurisdiction, or alternatively, they're negligible. And I think, a challenge here is that these models are all, if you will, predicting the average condition or expectation that will result. And I would note that the hydrologic impacts of the mine might either be worse than this or not nearly as bad. And there's not a way, I think, in the EIS process to revisit that question, for example, after the mine begins operation. I know that there's a mine up in the Tonto, I'm trying to remember I heard from the hydrologist from the Tonto Forest once about one of the mines up there, and when the mine opened, they had done all this analysis to look at the pumping impacts on some surface streams nearby. But it turned out when they turned the pumps on a long-term basis that the impacts were more severe than they expected. And that's in part, and surprises like that are likely to occur in hard rock aquifer systems like the one where this mine is. Because the Tucson Basin, the groundwater system underneath our feet here in Tucson, is relatively simple to understand. It's essentially a large bucket of sand and gravel. So water flows relatively easily through it. It's also relatively homogeneous and relatively easy for hydrologists to understand. But hard rock systems like the Cienega Creek Basin, the Santa Ritas, plus hard rock systems that are really complicated geologically. If you've ever looked at a geologic map of the Santa Ritas, the surface rocks expressions are changing every couple square miles. And those systems by nature are harder to characterize. And so, what I'd say is there's a high degree of uncertainty of what those impacts might be. And I don't think the EIS practice and system we have gives a way for that uncertainty to be communicated or to be, if you will, insured against. Like, what do you do if the impacts are worse and they're quicker? There's not a clear answer to me how that works in the EIS process. Let's see. I don't know if I fully answered your question, Larry, but, I don't think there really is a process to reconcile the results. There's ultimately a judgment, either by a judge or by the federal agencies involved and state agencies involved in permitting. I do believe that the Rosemont mine, Richard Carlson asked, this is sulfide ore. I do believe this is a sulfide ore deposit. I didn't refresh my memory on that, but they are gonna, leach this system. Most of the mines around here do some version of leaching and then concentration on either smelter or electroplating of their ore deposits. So what permits or processes the mine have to go through to demonstrate the impacts on ground or surface water? So they have had to get a 404 permit in the past for filling. They have to, they have to demonstrate what they have to, right? Environmental impact statement per se simply needs to lay out what the impacts are. And so it has to be a fair representation of what the impacts of the mine would be. But there are a variety of permits that the mine, again, I don't know the list of permits, if you will. I'm just a lowly hydrologist. I can understand what the hydrologic impacts are. And then there are these water quality concerns, as noted, right? If it is a sulfide ore deposit, there is tailings, there's potential for residual contamination going on into the future. And the biggest concern is always, sort of tailing waste floods, which occur rarely, but they do occur with mines around the world. Okay, no leaching. Thanks, Matt. I do believe both the county and the mining company have groundwater and surface water monitoring systems both in place and proposed, sort of regarding offsite impacts and also ground truth of modeling. And I think you'll see some of the ground truth of this modeling from Dr. McIntosh next month. I don't want to restrict her in terms of her statements, but she's trying to better understand the hydrology of the system using a variety of tools, and that should help refine future models or ground truth these models as they are. So, okay. Yeah, so Laura Norman asked sort of, right, there isn't a lot of, I think it would be good to get a better understanding of the actual system. Like I said, Dr. McIntosh's group is pursuing that with sort of geochemical techniques, tracer techniques. I think the challenge in this system is it's very expensive to get additional hydraulic and infiltration data for particularly through deep wells, right? Wells are expensive. It costs, an odd guess is, $100,000 for a 1,000-foot deep well. And, how many of those are you going to put in to understand the overall geology of the basin? There's a trade-off there. More information would certainly help, but what's the value of that information versus the cost is always a dilemma in studying the subsurface, because it's not, if we want to study a surface stream, it's pretty easy. We can go visit it, we can walk along it, we can make lots of measurements. The subsurface, even though it's not far away, my colleague Laura Condon is fond of saying the closest fresh water to where you're standing right now is in almost all likelihood groundwater, because even if you're in Tucson, groundwater is only about 100 meters below your feet. And if you look 100 meters on the surface, I don't have any surface water near my house other than those folks who have swimming pools. So the models do treat the climate as relatively static. So they're not, they do sort of build in some stochastic variability and the sort of decadal and annual variability we see, but they don't, they're really a steady state model. They're just sort of saying, take the climate we have and extend it. So, and arguably the mine itself is not entirely responsible for whatever prospective climate change we're going to have. So, but that would be a compounding effect. We do, in this region, we expect less winter precipitation, hotter, drier summers, and that's likely to result in decreases in recharge and increases of demand by vegetation for water. So, that would be a compounding effect. So, and yeah, there was a separate analysis to get a handle on those climate change impacts. I haven't dug deeply into that. So any other questions?
Hi, Tom. This is Cienega.
Yeah.
I just wanted to say that I am impressed that here it will take like 700 years to fill that pit, and in Panama it filled like just quickly. The pit in Panama with the low precipitation that is in there, it fills quickly.
Right. So the mean annual precipitation at the mine site is 16 inches or about 400 millimeters or so. So, one of the arguments the Myers model made was that the pit would never really get a lake, that it would not fill that high because evaporation rates would be so high. And I think the Montgomery Associates model makes a good argument for the numbers they use, which are a lower evaporation rate. But yeah, it still takes a long time. And part of that too in this system is that hard rock aquifer in all the models is expected to have a pretty, it has a pretty low hydraulic conductivity in all the models, and that's the expectation. So it'll take a very long time for the pit's effects to propagate out and eventually get to steady state. But most of the filling happens in a couple hundred years. But you're right. In Panama, it would happen 1 year. Yeah.
Yeah, we just have 2 years of operation in a copper mine in there, and it is already a lake.
Yeah.
The tailing management facilities is already a lake.
Yeah.
There.
Yeah. Cool. Are there other questions? Well, thank you. I hope I can help you with the groundwater system. Like I said, it's a complicated basin, and there are these other points. There are other things like surface water runoff, but I sort of focused on these long-term ones in part because I think this problem of capture is an important one to understand in general in our arid groundwater systems. That because it's true of residential or agricultural or municipal pumping of groundwater as well. The impacts aren't immediate, but they will last for a long time, and they take a long time to play out. And so they sort of speak to us to have caution in over extracting these groundwater systems because, impacts can occur, and then once they've occurred, it's going to take just as long for them to us to reverse them. So, yeah, thanks, Kita. Yeah, it is. The long-term impacts here are significant. And I think one of the keys when we think about mines, right, the metals we all using the metals. We're using them right now, right? A lot of the screens we're all watching, the electric lines and communication lines that communicated to us all use copper. And that's what this mine is going to extract. But on the other hand, the problems are permanent, right? Last fall, the Trump administration canceled a project in Alaska called the Pebble Mine because the mine was going to have essentially a similar effect on a large salmon fishery in the Bristol Bay watershed up in Alaska. And again, the argument was, yeah, on the one hand, the metals are needed, but on the other hand, this is a permanent impact to a valuable natural system. And I think the argument here in this region with Cienega Creek is largely similar. This is a fully intact aquatic system. And the biologists on the line, or biologists can tell you that those basically don't exist in southern Arizona. Almost all the freshwater systems have been invaded to one degree or another by non-natives, been dewatered, been otherwise impacted. And so the value of Cienega Creek is as this marker of this is what these systems operate like under natural-ish or as close to pre-development conditions as we can find. So